sirolimus is used to treat patients after kidney transplants. Not that that's important. On reaction with hot aqueous sodium hydroxide. So this is going to be a base hydrolysis. So it's a basic condition, but it's base hydrolysis. That is because what do we have? Do we have esters, nitriles, or amides? We have, well, these are ketones. This is the ester I was looking at. So that is the bond that we're going to break because that is the ester bond. And this one is ketone, this one is alkene, this one is alcohol, this one is ketone, this one is ether where the oxygen is in between carbon and carbon. This is ether, this is alcohol, these are ketone and hang on, this one is the amide. So this thing here is the amide bond. As you could see, this is a special kind of amide because it started from secondary amine where you have nitrogen there bonded to carbon. Okay, therefore you don't have any more hydrogen there. You have amide, ester, you're going to break there and there. So what is the structural formula of the product with the lower relative molecular mass? The rest of this molecule, if you think about it, the rest of this molecule is the one with the higher molecular mass. So when you hydrolyze this whole thing, there are no other ester or amide bonds to be broken. So therefore, this is the molecule with the larger MR. They're not asking for that. They're asking for the one with the smaller MR. So definitely the smaller looking molecule. So NH there. And then what I'm going to get is like that. And then COOH. Now I have a question here because this is base hydrolysis. I have just produced my carboxylic acid. The carboxylic acid will not survive. Instead, what I will get is O minus Na plus because this is a salt. Because carboxylic acid is acidic, I'm doing base hydrolysis. This is amine. Amine is base because amines are basic since it's got a lone pair that can accept H plus. They don't do anything in the presence of base for this base hydrolysis. So this is going to stay as amine. The carboxylic acid product is going to get deprotonated. So we will get a salt. That's the most important thing. We will get a salt. There is no salt there. And we know that the CO2 minus is on the next carbon to the NH there. The CO2 minus is next to the nitrogen, or I mean on this next carbon. They are not bonded directly to this one here. So this is wrong. This is also wrong because you don't get 2 times carboxylate. You only have one of these carboxylic acid group, and therefore you only have these being deprotonated. They always show it like that. In reality, the negative charge is on the oxygen. It's a carboxylate and it's an Na plus. I always make it a habit of writing down the ionic charges, especially when I know it's a metal salt. Okay, be very careful there. We reach this section B type of questions where these are the series of statements. The new syllabus from 2022 is going to scrub out this section B specifically. It does not mean that they cannot ask you section B type of questions. It just means that there will no longer be like exactly 10 questions. That is my take from what the syllabus says. Of course, in reality, you could have 11 questions. That is not section B. 11 questions of this type could happen. You could have 5 questions of this type could happen. There's no saying that it has to be the last 10 questions. It could be spread out over the rest of the paper. Could happen as well. All right. Anyway, we always check for statement number 2 based on the logic of these series of statements because no other combination of statements is used as a correct response. So question 31, which statement is about the phosphide ion and the chloride ion? This is counting protons, electrons, and neutrons. What I would do without even going through the options is to count them first. Phosphorus from the periodic table is element number 15, so 15 protons. Chlorine is element number 17, so 17 protons there. This is an ion. This is also an ion, so 15 plus 3 electrons because anion is when the atom gain electron. Minus 1 means you gain 1 electron. Therefore, 18 electrons, 18 electrons. Both of these have fully filled out the shell. They have the electronic configurations of argon, but they still retain the identity of being a phosphorus and a chlorine due to the number of protons not changing. The nucleon number, the number on top, the nucleons, or the mass number tells you how many protons you have and how many neutrons you have in the nucleus of an atom, whereas the proton number only tells you the number of protons. Therefore, to work out the number of neutrons, we have to take away the smaller number from the bigger number. We have 16 neutrons there. 35 minus 17, I get 18 neutrons there. So which statements are correct? Let's check number 2. Same number of neutrons. Well, 16 neutrons there, 18 neutrons there. Same is definitely wrong. Number 2 is wrong. Only number 1 must be correct based on this combination of statement. Same number of electrons, correct. Same number of protons cannot be correct, okay? They are different elements. So very clearly, different elements, different identity in the nucleus for the number of protons, and therefore different elements, different protons. Question 32, we have aluminium chloride, and we know it's sublime. Sublime is going from solid to gas straight away, relatively low temperature. So they're not saying that it has a very high melting and boiling point, they just say relatively low. That tells you that AlCl6 has a simple molecular, or if you don't like simple molecular, you can use the term simple covalent structure. So as we sublime, we just need to break the weak intermolecular forces between the molecule. That is why it doesn't require a lot of energy to overcome these weak intermolecular forces. So number 1 is definitely correct because it has intermolecular forces, weak intermolecular forces, relatively low temperature for the sublimation point there. Now, it does not tell you about the covalent bond strength because we are not breaking the covalent bond. That's the most important concept here. Not breaking the covalent bond. We are not talking about bond energy. We are talking about change of state here for simple covalent or simple molecular structure. Very, very important structure and bonding. We don't break coordinate or covalent bond there. We just need to break the weak intermolecular forces of attraction. Question 33, which statements are correct for all exothermic reaction? We know that delta H is lesser than 0. We know that in terms of system and in terms of the system, we draw the energy profile diagram and the progress of reaction or the coordinate, reaction coordinate. So the reactants have lost energy to the surrounding. That is why the surroundings will get hotter, but the reactant will have lost energy going to the products, and that energy is released to the surrounding. And we know that the surrounding, if you draw temperature against time, if this is a solution chemistry, you can draw a line there, and then it will go up, up, and then it will go down like that. So what you do is you plot a line there, and last but not least, at the time of mixing, you don't record the temperature, but that is the extrapolated highest temperature. This is the initial temperature. Your delta T will allow you to do Q equal to MC delta T, and from there you can work out backwards to get the enthalpy change for the reaction. Going to the options, on the reaction pathway or reaction profile diagram, your products are shown lower than the reactants because you have energy on the y-axis, so the products have lower energy than the reactants as the reactants lose energy to the surrounding and the surrounding gain the energy. That's why your surrounding temperature would have increased there because the system released heat energy to the surrounding. So 2 is correct there. The products are lower in energy than the reactants. The delta H for the reaction is negative. That is correct. What about number 3? The reaction will happen spontaneously. You can't tell because this is actually an A2 concept. I don't know why they ask you in AS, but spontaneous reactions are when delta G is lesser than 0. Delta G is not delta H. This is called the Gibbs free energy change in the Gibbs free energy. So delta G in A2 is equal to delta H minus T times delta S. Just because you're exothermic does not mean it's spontaneous because it also depends on the entropy change, and this is A2 concept and this is also A2 concept. The enthalpy is AS concept. Okay, so you cannot tell whether a reaction will happen spontaneously or not just from delta H alone. Okay, and you have to incorporate the idea of delta S as well. So 1 and 2 must be correct. That's option B there. Question 34, we're looking at redox reactions. So which of the following is a redox reaction? I can tell number 2 is redox reactions. If we look at SO2, we only look at one unit when we look at oxidation number. So the whole molecule is uncharged, meaning the oxidation number of the molecule is 0. Sulfur plus 2 times minus 2. The sulfur there is plus 4. SO3, you have 0 for the whole molecule. Sulfur plus 3 times minus 2. Sulfur there is plus 6. So you do get oxidation there. So what is being reduced there? Because you don't see any electrons there. That is because the oxygen is 0, going to oxygen minus 2 there. Sulfur sulfur in the SO2 has been oxidized. The oxygen in the oxygen has been reduced in decreasing its oxidation number from 0 in O2 to -2 in SO3 there. Okay, so hopefully you can see that that is definitely a redox reaction there. So let's have a look at some easier one. So number three is the last step in the formation of acid rain. It's also the last step in the series of industrial processes to make, to have the human or man-made sulfuric acid in the industry. SO3 is sulfur plus 6, as we mentioned just now. H2SO4 is sulfuric acid, is sulfur plus 6. If you don't believe me, H2SO4 or SO4 2-, they have sulfur plus 6. Let's try and show for the H2SO4. 2 hydrogen, each hydrogen is plus 1. Sulfur there, one of the 4 times the oxygen, each of which is -2. Sulfur is -2. Move the plus 2 to the other side, become -2. Move the -8 to the other side, become +8. Sulfur is plus 6. You could also try from the 2-, where the oxidation number of the ion is the charge of the ion. So -2 equal to sulfur plus 4 times -2. Sulfur is -2 plus 8. Sulfur is plus 6 there. That's because sulfuric acid 2H plus, and then you get this ion from this thing. So these and these will have the same oxidation number, sulfur plus 6. Because this gives this will give you that as well. Now this is not a redox. Last one is not a redox reaction because there's definitely no changes in the oxidation number of the sulfur. 2 is correct, 3 is wrong. I can only have one answer, which is 1 and 2. So there's option B there. I'm just gonna go quickly to the last one. Oh yeah, okay, I was just worried that I made a mistake in the last one because I said 1 and 2, so there was option B. So this is 1 and 2 only, because by checking number 3, which is the easier one, because I know this chemistry from the top of my head, I know that this is definitely not a redox. I've just shown you that there are no changes in the oxidation number going from SO3 to H2SO4. You can check, of course, for option 1 if you want to. This is nitrogen 0 as an element in N2. In NO, what we get is nitrogen must be +2 since there's one of it, and oxygen is -2. In NH3, the nitrogen is more electronegative than the hydrogen. The hydrogen is +1 oxidation number. The whole molecule has 0 charge, so nitrogen is -3. This is a classic disproportionation, but rather than one species getting both oxidized and reduced in the same reaction, this is actually what you call reverse disproportionation. So you can think about your case study on disproportionation. This is like the reverse disproportionation, as 2 species here, one get reduced, +2 to 0 is a decrease in oxidation number, there's reduction. And this is a negative oxidation number increasing to 0, there is oxidation being increased in oxidation number there. Question 35, when we add it to water, which one will cause a change in the pH of water? SiO2, just like Al2O3, is insoluble in water. If it's insoluble in water, it will not cause any pH change in the water. That's why it's still pH 7. Same thing with Al2O3, still pH 7 because the oxides are insoluble in water. 1 is wrong, therefore there can only be one answer, which is 2 and 3. Now in terms of exams, you can move on, but I'm doing a tutorial. My job is to show you that the underlying chemistry behind it. You're going to get calcium hydroxide, the pH is above 7 there. Not very soluble, but at least more soluble than magnesium oxide, as the solubility of the group 2 hydroxide increases down group 2. SO2, oxide of non-metal. This is SO2. Previously you had SO3, giving you H2SO4. This is SO2. SO2 is sulfur plus 4. What you're going to get is a sulfur plus 4 acid. This is a sulfite ion. Sulfite ions were stated, and you learned this in the year 9, year 10, qualitative analysis. They were not in your practical, but they were in the theory syllabus. If you don't believe me, go back to what you have learned, learning objective from your previous syllabus when you were doing 14 to 16 years old chemistry. You will see it in the theory syllabus, in the theory part of the curriculum. So that is -2 equal to sulfur plus 3 times -2. Sulfur there is -2 plus 6. Sulfur is plus 4 there, and there is no changes in the oxidation number going from here to here. This is just dissolving in water, and it will give you H2SO3, just like it gives you the SO3 2- from the H2SO3. Sulfur plus 4, going to sulfur plus 4. That is an acid, that is a base, So this acid there, the pH is way below 7 there. Question 36. So we have halogenated hydrocarbons. There are some uses. There are also some dangers associated with them, such as the destruction of ozone layer as a result of free radical substitutions. Carbon-chlorine bond can be broken in the upper atmosphere with a series of free radical reactions. So what have these halogenated hydrocarbons been used for? Meaning to say halogenated hydrocarbons, or they can say uses of halogenoalkanes. So they are polar as a result of the carbon halogens having quite a big difference in electronegativity. As a result of their polarity, they are useful as solvent to dissolve polar substances. Polar solvent dissolve polar substances. Non-polar solvent dissolve non-polar substances. So refrigerants, we do use them as refrigerants, but these days a lot of the refrigerants in air conditioners or freezer, they no longer uses the CFC, the chlorofluorocarbon. Instead, they use some other halogenated compound. Monomers in the polymer manufacture, that is true, because if you think about polyvinyl chlorines, that is your PVC, used for making PVC water pipes, like those plastic pipes. They are not polyethylene, they are PVC, polyvinyl chloride. It comes from this monomer, which is just alkene with one chlorine, and when you polymerize it, you're gonna get like that, and I'm gonna have a Cl like that. So basically, there's a Cl there, lots of double bond. Now there are all single bond in this polymeric chain there. All three are uses of halogenoalkanes, and therefore A is the only answer there. The next thing is, in which structures do the 4 carbon atoms lie in the same plane? You're just looking at the carbon atoms, label C. Label C. Okay. What in the world is this? The carbon atom, label C. Which one lie in the same plane? So we look at the central carbon. Always look at the central carbon. Okay, if we look at the central carbon, there is 3 bond pair and 0 lone pair. You only count the sigma 1, 2, and 3. So 3 sigma bond, 3 bond pair. The carbon there form 1, 2, 3, and 4 covalent bond. So there's 0 lone pair. So this is a trigonal planar geometry, 120 degree. And as you know, therefore as a result, this is definitely planar. And these 3 are connected to this. So they must be planar by extension or by bonding to this center one. 2 is correct. How about number 1 here? So this is a single bond. You see, this is a single bond. If I look at this central carbon here, this is 3 bond pair and 0 lone pair as well. Count the sigma. Only 1 sigma, 2 sigma, and 3 sigma. And this thing is also trigonal planar at that central carbon there. And because that is also true for this carbon, they haven't shown you the hydrogen, but 1, 2, 3, there is another hydrogen which is not shown. That is also the same idea for both. For both of these carbons, they must be planar like that. And by extension, yes, it could be tetrahedral here, but if we're just looking at the carbon, the 4 carbon must be in the same plane, as this is bonded to this trigonal planar carbon. This is bonded to this trigonal planar carbon. So trigonal planar carbon there, trigonal planar carbon there. So 1 is also have the 4 carbon atom label C there in the same plane. How about this next one? We have a carbon with 1, 2, and 3. So around that central carbon, around this central carbon, there are 3 bond pair, but there is 1 electron, isn't it? There must be 1 hydrogen there. Okay, they haven't shown you the hydrogen. They haven't shown you the hydrogen. It must have 1 hydrogen. Must have 1 hydrogen. But anyway, let me just have a look here. This one has 2 hydrogen. This one has 2 hydrogen. So we're looking at tetrahedral carbon, and tetrahedral carbon. So around those things there must be 4 bond pair and 0 lone pair. They are tetrahedral carbon, which is carbon sp3. They cannot be planar there, even though you have a planar carbon there, which is the one underneath here. This is definitely sp2, trigonal planar as well, 120 degree. But that thing there's tetrahedral, they are no longer in the same plane, I think. Well, let's have a look. Yeah, basically like because of these being tetrahedral there, so that means this is no longer planar, it's no longer flat together with that. So even though this is flat with that, but this will no longer be flat with these carbons. As a result, tetrahedral around this central carbon here, meaning to say in number 3, these two carbons are not in the same plane as these two carbons. Well, not in plane as this carbon actually. These two are not in the same plane as this carbon, and therefore not all 4 of them are in the same plane, and therefore only 1 and 2 must be correct. That's option B there. Question 38, which statements about 2-methyl butane 1-ol. So start from these 4 carbons and then the OH at carbon 1. So draw 4 carbons, 1, 2, 3, and 4, or the other way around, and I add in the OH. I have a methyl, which is a CH3 at carbon 2, so draw a branch CH3 there. So 2-methyl butane 1-ol. So which one is correct? Can you oxidize it to give an aldehyde? I'm just checking number 2 first. So when you have oxidizing agents, like the orange color acidified dichromate, so example H plus Cr2 or 7 2 minus, orange color dichromate 6, that's chromium plus 6, and then you reflux this. Can you get an aldehyde? Well, they want an aldehyde, so I don't reflux it. Therefore, I had to heat and distill immediately if I want to get the aldehyde, and I can get it because this carbon with the OH is bonded to one other carbon. This is a primary alcohol, so you can oxidize it to an aldehyde if you heat and distill immediately. Number 2 is correct there. It can give HCl when you react with PCl5. When I react with PCl5, it's actually a reactant, and this is how you form the halogenol alkane. And having done that, I will remove a HCl and I'll get POCl3. So 5 chlorine, 3, 4, and 5, and the oxygen from there comes from the OH, and the H from there goes to the HCl, steamy white fume exothermic reaction. So you do get the steamy white fume HCl gas there. Now this alcohol exists in 2 optically active form. Optically active there, 2 of them, because you get non-superimposable mirror images. These are the definitions of enantiomers. Basically what you get is you get enantiomers, the 2 non-superimposable mirror images of each other, and they arise as a result of a carbon bonded to 4 different groups there. I don't show you the hydrogen, but there is 1 hydrogen there because carbon form 4 bonds, 1, 2, and 3. There's 1 hydrogen there. There's this group that has alcohol. There's this group that don't have alcohol, 2 carbons. There's this group here that has 1 carbon there. Methyl, ethyl, hydrogen, and something that has alcohol. So you do have a chiral carbon. Usually we put an asterisk on it. So yes, there is chiral center, therefore you can get optical isomers there. Question 39 is about this mechanism. So this is between an aldehyde and a ketone with nitriles, with HCN actually, that is your reactant. But of course, that is not strong enough as a nucleophile. That is why you need a NaCN or KCN catalyst, because a catalyst is not used up in the reaction. So be very clear about the role of the catalyst. These are ionic form, so they will kickstart the reaction from the lone pair on the Cn-, attack the delta plus carbon, and heterolytic fission will break this carbon-oxygen bond, giving you the 2 electrons to the oxygen. The oxygen now has a negative charge, but it also has a lone pair on the oxygen, and that will attack the polar HCN. Earlier we talked about the HCN not being nucleophilic enough, but it is polar. As a result of it, from the lone pair, protonates and another heterolytic fission and return these 2 electrons, this lone pair, to Cn-, and that is why you regenerate back the Cn- at the end of the reaction. It's a catalyst, it's not used up. The original Cn- might no longer be the Cn-, but no matter what, you will always give back a Cn- at the end of your nucleophilic addition mechanism. It is an addition, it is a nucleophilic addition mechanism, which means the type of reaction is addition reaction. The Cn- is the one which is attacking, rich in electron attacks poor in electrons, so it's not an electrophile, it's the aggressor, it's the attacker. If you are the attacker, you are electron rich, rich attack poor. 2 is correct, 1 is wrong, you can only be left with option C there. As I did mention, heterolytic bond breaking, I use full-headed arrow, the 2 electrons go to the oxygen, you have lone pair there, the 2 electrons break there, heterolytic fission, the 2 electrons go to the carbons. This is unequal splitting of the covalent bond such that the 2 electrons in the covalent bond go to only 1 atom. Instead of, like in free radicals, homolytic fission, you have equal splitting of the covalent bond, you get radicals. Here, you don't, because heterolytic fission, heterolytic bond breaking always give you cations or anions. The last question in this paper, we have monopotassium citrate and blah 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 blah. Which statements about this is correct? It can act as a dibasic acid. Well, it can act as an acid, that's the first thing, because there is one there and there's two there. This thing is no longer acidic and the alcohol is not acidic. So that means dibasic means it can react with 2 moles of OH minus, and therefore it can give you this thing here, CO2 minus, K plus, and I don't know about this, but I don't know about the base being used, but it can be deprotonated if I have 2 moles of that OH minus, and I will now get 2 mole of H2O. So yes, it can act as a dibasic acid because it can react with 2 moles of OH minus for 1 mole of this compound here, monopotassium citrate. It does not have a chiral carbon. It does not. Okay, they bother for you. This is a negative statement. That is correct because this group, this green color group which I have circled, and that group, they are the same. If they are the same group, this carbon is not chiral. Not chiral because you don't have 4 different groups attached on the carbon. So it does not have a chiral carbon. It's correct. Okay, be very careful. This is correct. It reacts with NaHCO3. So this is hydrogen carbonate. Hydrogen carbonate behave just like carbonate ions. So that means if you have acid, then you're going to react with carbonate because carboxylic acid plus carbonate is the same as carboxylic acid plus hydrogen carbonate, and they will give you carbon dioxide, salt, and also water. So they will also give you carbon dioxide, water, and also metal salt from your metal hydrogen carbonate there. So 1, 2, and 3 are definitely correct. That's option A there. Okay, we've reached the end of this paper 1-2 for the June 2015 AS level multiple choice question for these 16 to 18 years of curriculum. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel, and do follow me at ptet.chemistry. That's at ptet.chemistry. Facebook, Instagram, Twitter, and Telegram to get connected. These full yearly paper tutorials are only available for the silver tier members, and they cost only about a cup of coffee. So do support my work and do spread the words about the channel so that other people can learn and enjoy these tutorials available on my channel as well. Thank you for watching. I'll see you in the next tutorial.